Welcome to this explainer on elementary programming concepts. You know, if you've ever stared at a really complex piece of software and just wondered, how does this actually work under the hood? Well, you are absolutely in the right place. Today we're going to demystify exactly how we as humans successfully communicate with computers. We're going to strip away all the magic and really look at the fundamental logic and structures that make literally all software possible.
Okay, let's just dive right into the biggest puzzle of computer science. How do we actually talk to a machine that only understands ones and zeros? See, at their absolute core, computers are built to execute instructions in what we call machine language, and that is a language made entirely of binary code, literally just ones and zeros. Now, obviously, humans don't dream in binary, so we desperately need a bridge to translate our human concepts, our math, and our logic into the exact binary that the hardware actually needs to function.
So how do we cross that massive communication gap? Well, on one end, we have machine language, right? The native tongue of the processor. But on the other end, we have high-level languages. These are problem-oriented languages, things like C, Fortran, or COBOL. When we write in a high-level language, we get to use words and mathematical symbols that actually make sense to us. And we bridge the gap between the two using a really vital tool called a compiler. Think of the compiler as our ultimate translator. It takes our human-readable, high-level code and crunches it all the way down into the precise machine language the computer can actually run.
Our journey today takes us through 5 key stages. 1. Talking to computers. 2. Thinking like a programmer. 3. Data and memory boxes. 4. Writing your first program. And finally, 5. Testing and debugging.
Let's kick things off with part 1, talking to computers, and take a quick look at the evolution of instruction over the decades.
It really is incredible to see how much easier we have it today. Back in the 1940s and 50s, early programmers literally had to think like the machines. They wrote programs entirely in tedious, mind-numbing binary ones and zeros. Imagine having to remember that the number you wanted to use was stored at memory location 1000111011011011. Honestly, no thank you. To make life just a little bit easier, assembly language was created, which used short mnemonic codes like add. But the real game changer hit in the late 1950s and 60s with high-level languages. Thanks to compilers, programmers were finally freed from worrying about the specific hardware quirks of their machines. They could finally just focus on solving the actual problem in front of them.
Which brings us nicely to part 2, thinking like a programmer, also known as the blueprint.
Because here's the thing, before you even type a single line of code, you need a logical blueprint. How a computer solves a problem follows a very clear, deliberate pipeline. You don't just sit down and start mashing keys. First, you have to define and analyze the problem to ensure you have the absolute clearest understanding of the requirements. Second, you develop an algorithm. Third, you finally write the computer program based on that algorithm. Fourth, you hunt for errors by testing and debugging. And fifth, you document and maintain the program so other people can actually use it. This structured approach, that is exactly what separates good programming from totally chaotic guesswork.
So, let's zoom in on that crucial second step, developing an algorithm. What is it? Well, an algorithm is essentially a highly specific recipe. It contains input instructions for getting data from the outside world, processing instructions for manipulating that data using math or comparisons, and output instructions for delivering your results. It dictates exactly how the computer should act. In our daily lives, we use algorithms all the time, like looking up a word in a dictionary or following the steps to change a tire. In programming, it is the exact same concept. We're just applying it to data.
But to actually process that data, a computer program has to have a place to store it. And that brings us to part 3, data and memory boxes, the architecture.
Think of computer memory not as some vast invisible cloud, but as a set of physical storage boxes. Each box can hold exactly one item of data at a time. And to find these boxes easily later on, we stick a label on them. In the programming world, that label is called a variable. So, if we're writing a program to calculate the area of a square, we might label one box S for the length of the side and another box A for the resulting area. And remember, if we put a new value into a box, the old one is completely erased. It's gone for good.
But here's the catch. You can't just throw anything into any box. These memory boxes have to be explicitly declared to hold specific data types. If you want to store whole numbers, like 3 or -52, you declare the box as an integer. If you're dealing with money or precise measurements that require decimal points, like 199.95, you use reals, which are also known as floating point numbers. And if you just want to store a single letter or a symbol, you use a character data type. Telling the computer exactly what kind of data to expect is absolutely fundamental to writing a working program. All right. Now that we understand our algorithms and our memory boxes, we can transition right into Part 4, writing your first program, which is the execution phase.
Let's actually translate these concepts into the precise syntax of the C programming language. Here is where it all finally comes together. This small C program successfully calculates the area of a square. First, it declares our integer variables a and s, so essentially building those physical memory boxes we just talked about. Then, it prompts the user to enter the length of a side. It reads that input, stores it safely in the S box, and then does the math, side multiplied by side, right inside the code, before finally printing the calculated area back out to the screen.
To actually perform that math and shove a value into one of our memory boxes, we use what's called an assignment statement. And it's beautifully simple. An assignment statement is just a variable on the left, an equal sign in the middle, and a value on the right. For example, a equals 14. But a quick tip for programming logic, you should actually read this in your head as a becomes 14. It takes the value on the right and assigns it securely into the memory box labeled on the left.
So once our program has done all its heavy lifting and calculations, we need to get our answers out of the computer and into the real world. We do this using output instructions. In C, the standard way to do this is with the printf function. If you want the computer to display "Welcome to Trinidad and Tobago," you simply pass that string of text straight into the printf function, and boom, it prints it directly to the user's screen.
Now, when you start trying to format that output to make it actually look nice, you're going to quickly discover a weird quirk about the printf function. It doesn't automatically drop down to a new line when it finishes printing. If you print two things in a row, they'll just smash together on the exact same line into this unreadable mess. To fix this, we use special escape sequences inside our text strings. The most common one you'll use is \n. Whenever the computer sees that \n, it stops printing text and immediately jumps the output cursor down to the left margin of a brand new line. Problem solved.
C also lets you leave little notes for yourself right inside the code using comments. You can use a // for a quick single-line note or a /* for longer multi-line explanations. Now, why is this so important? Because a comment has absolutely zero effect on how the program actually runs. The compiler completely ignores them, but they are incredibly vital for human readability. They explain your logic to your future self, which, trust me, might just save your sanity when you're trying to figure out what on earth you were thinking 6 months down the road. Or it helps the next programmer who gets stuck maintaining your code.
So, once your code is written and compiled, you might think you're totally done. But nope, we have to move to Part 5, testing and debugging, finding the flaws.
As a programmer, you're going to face bugs. It's just a fact of life. And these bugs usually fall into two distinct camps. First up, syntax errors. This happens when you break the literal grammatical rules of the C language, like forgetting a semicolon at the end of a line or spelling a command wrong. The compiler will catch these and just outright refuse to build your program. But far more dangerous are logic errors. A logic error happens when your program perfectly follows the grammar rules, so it runs totally smoothly, but it produces the completely wrong answer. Like, say, you accidentally typed a plus sign instead of a multiplication sign. The area of a square with a side of 10 would calculate as 20 instead of 100. The computer did exactly what you told it to do, your logic was just flawed.
So how do we catch those incredibly sneaky logic errors? By rigorously testing. We run what we call known test data through the program. If you input a side length of 10, you know for an absolute fact the answer should be 100. If the program spits out 20, you instantly know you have a logic error that needs fixing. And once all those errors are pinpointed and corrected and the program is working flawlessly, then you finalize your technical and user documentation. That way, the people actually using your software know exactly how to operate it.
So, as we wrap things up here, you can really see that programming isn't some kind of incomprehensible magic. It's just highly specific, carefully structured problem solving. It's all about translating human intentions into precise, step-by-step algorithms, storing our data in labeled boxes, and executing instructions flawlessly. Honestly, it makes you think differently about how everything around us is accomplished. Which leaves me with a question for you. If programming is fundamentally just structured instruction, what complex daily task in your own life could you break down into a step-by-step algorithm today? Think about it. Thanks for joining us on this explainer, and keep exploring the logic behind our digital world.